PFAS, also known as per and polyfluoroalkyl substances, are a very interesting chemical of concern right now. If CFCs were the chemical of concern in the 80s and 90s, PFAS would be the chemical of concern now in the early 21st century. A lot has come out about the effects it has on people, animals, and the environment, and it is important to see how PFAS works and for us to understand what PFAS is. PFAS was invented in the 30s and became really ubiquitous around the 50s and 60s, and it still persists today. So today I will present about PFAS and the structures and the functions of PFAS and the impacts PFAS has on society, the environment, and on health. The full name of PFAS is per and polyfluoroalkyl substances, and it is a broad class of fluorinated chemicals. On the graphic on the right, we can see that is divided into non-polymeric and polymeric PFAS, and then there are subclasses and groups of PFAS beneath these classes. PFAS is especially used in industrial applications and consumer products. That is stemming from the invention of Teflon in the 30s. Common individual PFAS that we see in scientific literature and in the media are PFOA, PFOS, PFHXS, and PFBS. And these are really common PFAS, as well as a multitude of other PFAS that you can see in the literature and in the media. There are also actually many definitions of PFAS owing to operational context, and I will get to that in the next slide. So in a lot of the nomenclature for PFAS, there are actually a lot of working definitions based on scientific papers and different organizations. There are different contexts on which PFAS is discussed. So we have these scientific papers and then these various organizations that talk about PFAS. The simplest definition out of all of these is the legislative definition from different states, and it's that organic chemicals containing at least one fully fluorinated carbon atom are considered PFAS. A lot of the legislation and regulation is built around that definition. Uh, there is a new definition, an operational definition coming from the OECD that is being discussed in the scientific community because it expands PFAS a lot. It is estimated that over 7 million compounds are considered PFAS under this definition. So PFAS has various physical and chemical properties. One of these properties is that it's usually solid at room temperature, most of these PFAS, but some PFAS are actually liquid at room temperature. And we can owe this to the length of the fluorinated chain of certain PFAS molecules. Generally, the longer the chain, the higher the melting boiling points, and that's why some PFAS are liquid at room temperature because they have shorter fluorinated chains. A lot of the other physical properties are dependent on this length, such as in long chain PFAS, it affects how they bioaccumulate in humans, but we'll get to that later. PFAS is also extremely stable thermally, chemically, and biologically. So PFAS has a high resistance to degradation and oxidation because of its stability. This is why it's so prevalent in the environment and it's really hard to get rid of. PFAS also has amphiphilic structures and functions. PFAS has surfactant behavior because of its amphiphilic structure. PFAS has a hydrophilic head and hydrophobic tail. This is reminiscent of the phospholipids in cellular membranes, but in this case, PFAS has a hydrophobic fluorinated tail, while the head is a polar functional group. And each PFAS is different because of different quirks, and the functional groups also dictate a lot of the function of PFAS. It's important to remember that structure equals function. So the general structure of PFAS is based on fluorinated tails and the functional groups. So you can see in that graphic on the left, uh, There is a hydrophobic fluorinated tail, and that can vary in length. Uh, and the PFAS molecules usually have a hydrophilic polar head, and that can be fulfilled with various functional groups. For this example, they list three functional groups, but there are many more that can take place. And this graphic specifically talks about general non-polymeric perfluorinated substances. So just to keep that in mind, all PFAS have a presence of fluorine and the carbon-fluorine bond, and that is how a lot of the properties of PFAS arise. Fluorine, by its own merits, have characteristics that contribute to the structure and function of PFAS. So fluorine has high electronegativity, and that contributes to thermal and chemical stability, as well as strong acidity. Fluorine is also a very small chemical. It has extremely small atomic radius, so that contributes to chemical stability. Fluorine has low polarizability, which means it has weak intermolecular forces, and that contributes to the surfactant behavior. Uh, PFAS is actually stronger with the surfactant properties compared to traditional hydrocarbon surfactants because of the presence of fluorine. And fluorine has a high ionization potential, which means it's hard to remove the electrons, and this contributes to the resistance to degradation. The carbon-fluorine bond strength also contributes to the resistance to degradation because the carbon and fluorine bond is one of the strongest single bonds in chemistry. PFAS is a broad class of chemicals, which means that there is a lot of diversity in structures. In the graphic on the right, we can see that non-polymeric PFAS and polymeric PFAS have different uh, structural uh, structural quirks. So non-polymeric PFAS are usually shorter molecules. They have shorter chains compared to polymeric PFAS, and they also have the presence of functional groups, usually with a hydrogen as well. Polymeric PFAS, on the other hand, are much larger and longer than their non-polymeric siblings. For example, in Teflon, the backbone is actually super long. We can see this in the brackets and the subscript N in the actual graphic. This means that this chain will repeat for as long as N dictates it is. And uh, Teflon, uh, Teflon and its siblings, fluoropolymers, um, actually don't have hydrogen, so it's strictly fluorine. And in D, there is the inclusion of oxygen for that class of chemicals. Side chain fluoropolymers are also a prominent PFAS class. They do have non-fluorinated backbones, so usually that is a hydrocarbon backbone, but they do have fluorinated side chains, so that is attached to the chemical, non-fluorine molecule that is attached to the backbone, and we can see that in the green boxes on the graphic there. PFAS has many current applications, the most notable of which is firefighting foams. It is a major source of contamination in the environment, but it is effective in fighting fires. PFAS is also used in fast food packaging, and it's also used in non-stick cookware, and those two are of uh, high concern because of the exposure to food. It is thought that the usage of PFAS in these consumer goods is how PFAS has permeated into humans and the bloodstream. PFAS is also used in textiles and clothing, such as in waterproof clothing and coats and stuff like that. PFAS is also used in paints and in trace amounts in personal hygiene products. We can see in the graphic on the left that these various consumer goods and also the industrial applications, such as uh, the factories and pesticides, uh, contaminate wastewater facilities and agricultural areas. And all in all, this contamination, in addition with consumer goods, creates the human exposure aspect of PFAS. PFAS is thought to have a lot of adverse health effects. This is due in part to the similar structure to fatty acids. PFAS easily binds to albumin, and by association, it also binds to different proteins in the body. Because of its similar structure to fatty acids, this is why it is a metabolic disruptor and endocrine disruptor. It is also important to note the difference between long chain PFAS and short chain PFAS. These are actually quite different in their mechanism of action. Long chain PFAS are more bioaccumulative in humans, while short chain PFAS are actually more mobile, and this is how it spreads out to remote areas in the environment because it has high mobility. PFAS is a notable metabolic disruptor. It affects PPARs, which regulate lipid metabolism, glucose homeostasis, and other metabolic functions. PFAS has endocrine disrupting properties, and it can alter the levels of sex hormones like testosterone and estrogen. It is thought that it is possibly carcinogenic for these reasons. PFAS was invented in the 30s with the invention of Teflon, and the invention of Teflon paved the way for Minnesota-based companies DuPont Corporation and 3M to manufacture various products and pure PFAS compounds. This caused the persistence in the consumer goods later on during the 50s and 60s, as in the post-war boom, a lot of synthetic chemicals were used in these newfound consumer goods, and they were used for that purpose. In the 60s, a lot of PFAS products were actually disposed and buried in Minnesota by both companies. And around the same time, there were internal inquiries about the toxicity of PFAS. 3M actually knew that PFAS was toxic because they performed tests on monkeys. And DuPont toxicologists also said that it might have been toxic. The disposal of PFAS by these companies resulted in the Superfund site, the Oakdale dump. Around the 80s, the Oakdale dump was created after the EPA was alerted of hazardous waste. After the Oakdale dump was created, the 1980s and 90s increased the awareness of PFAS toxicity, and 3M and DuPont were under a lot of fire for hiding these properties of PFAS, and this raised the public awareness of it. In the 1990s, the first scientific papers on PFAS were released, and in one of the graphics onto the right, the top right, it talks about this landmark paper about occupational hazards with PFAS and how a lot of workers had increased risk of cancer. The backlash on PFAS caused a decrease in the production of PFAS and the rollback, as well as regulation on PFAS, but PFAS production is still ongoing. There are still a lot of studies on PFAS being done. A lot of the effects are still not known. The underlying mechanisms to them are still unknown. PFAS exposure is vast, and most humans are actually exposed to PFAS. So PFAS has a huge environmental impact as well. The properties of PFAS affect the bioaccumulation and degradation. As I mentioned earlier, long-chain PFAS bioaccumulate in humans easier, while short-chain PFAS are actually more mobile and spread throughout the environment quicker. This is how it gets to really remote areas because of its mobility. We see that in Barhana et al. 2024. The ubiquitous contamination of PFAS in most places has been a impact on the environment. The presence in runoff, soil, and more is due to the industry and firefighting. And environmental remediation methods are expensive. They're not cost effective. Uh, there are methods such as soil cleanup, which is done through combustion, or washing, which is a novel method. Incineration is the most common remediation method in the environment, but is thought to release more chemicals in the air. The societal impacts of PFAS are huge. There are a lot of health implications due to the ubiquity of PFAS. Because of this, it is highly publicized in the media, and there is a lot of public awareness of PFAS. PFAS remediation is really expensive and sometimes difficult. For example, in Minnesota, where a lot of the PFAS manufacturing happened, it is estimated that 14 to 28 billion dollars will be spent cleaning up PFAS and wastewater, which is unattainable for most estimates. PFAS is also in the soil in most places due to agricultural applications and firefighting. It is really difficult to remediate and degrade PFAS in the soil because combustion is not really effective in incineration, as well as the novel method of washing. Many things are still unknown about PFAS. A lot of the underlying mechanisms for the effects of PFAS are still unknown, and the scientific community is still working to figure out a lot of things about PFAS. And in the future, we must have to deal with the persisting human exposure to PFAS.